Hello everyone. Today we're going to work on a 2 degree of freedom system. In this video, I'm going to go with the multi-body template. I'll start with adding a prismatic joint to the model. This joint will represent spring, and I'll use solid blocks to represent the masses. Then I'll add another set of the same components. By default, the prismatic joint only allows motion in the z direction. So I'll rotate it 90 degrees around the y-axis to allow movement in the x direction instead. Next, I'll set the stiffness in the internal mechanics tab. Alright, for the masses, I'll specify them as point masses. It's already set to 1 kilogram, so I'll leave it as is. Since we have two masses, I'll change their color to avoid confusion. Let's go with red for this one, and apply the same values to another set of components. And blue for this one. Alright, for the excitation here, I'll use an external force and torque block. Alright, the coordinate system of this block depends on the follower. I'll select the z direction, which maps to the x direction in the world frame because of our earlier rotation. For the actuation force, I'll use a harmonic. Add a sine wave to the model. Since each mass is only 1 kilogram, I'll apply a small amplitude force. Then add a sensor to measure the position. Use the world frame and select the x direction. And change the unit of a converter. I'll add a second sensor for another mass as well. Alright, let's see the result. As you can see, these two masses overlap. To fix that, I'll use a rigid transform to separate them. I think 2 meters might be good. Alright, let me tidy things up here for a second. This doesn't affect how the system works, but I like to keep things clean and easy to follow. Since we shifted it by 2 meters, we also need to transform it back before connecting it to the sensor. Otherwise, the position will be measured relative to the offset. Let's see. Now you'll see a clear gap between these two masses. What happens if we don't translate it back? From the time response, you'll notice it oscillates around the offset position, exactly 2 meters off from the reference. Alright, now let's try changing the excitation frequency. This 2 degree of freedom system has 2 natural frequencies and 2 mode shapes. Let's apply the first natural frequency and observe the motion. I'll add this to compare the responses. Here we go. As you can see, these two masses move in phase, but with different amplitudes. All right, let me show you a graphical visualization. You'll see that mass M2 moves slightly more than mass M1. If you measure the values, you'll see that they match the first mode shape. Now let's try exciting the system at the second natural frequency. You'll see the out-of-phase motion, with mass M1 moving slightly more than M2. If you take a look at the time response, you'll see it clearly. As you can see, the responses are out of phase, and a response x2 has a lower amplitude than x1. Alright, now let's check out the free vibration by setting the initial positions. First, I'll turn off the force. Then, I'll use the state targets to assign the initial positions. In this case, I'll set x1 to 0.2 meters and 0 for x2. For another spring, you can't just leave it at 0, because this is a kinematic chain. Moving one spring affects the position of the second mass. So if you stretch the first spring by x and leave the second spring at 0 deformation, both masses will shift by x. To keep the second mass at 0, you need to assign a counter deformation in the second spring. Alright, let's see the results. You'll see the system oscillate with this initial offset. Okay, now let's try using a mode shape as the initial conditions. First, I'll use the first mode. Here we go. You'll observe a pure mode motion, with both masses moving in phase and with the correct amplitude ratio. Let's verify it by measurements. x1 is 0.2, and x2 is around 0.324 meters, which gives us a ratio of 1.618. If you take a look at the graphical plot, it clearly shows the mode shape behavior matching the time response we just observed. And since there's no damping, the system will always behave like this. Okay, if we plot a phase portrait of x1 versus x2, you'll get a straight line with a slope of the amplitude ratio like this. If you measure the values and determine a slope, you'll see that the slope matches the mode shape. Now, if we use the second mode as the initial condition, the phase portrait will show a slope of negative 0.618, showing the out-of-phase motion. As you can see, it's a negative slope line. You can check the slope by yourself. Now let's check the oscillation frequency. In this case, we expect the second natural frequency. I'm going to use the consecutive peaks time difference. So it's 1.618 radians per second. As you can see, it's not an exact match, but it's close enough. I hope you found this helpful. If you have any questions or want to see a specific topic, let me know in the comments. Thanks for watching, and I'll see you in the next video.